Dear students, today you shall be learning from the module about the following points. You shall learn about the Metallocenes and their basic structure, know about the structure of cyclopentadiene and its involvement in Metallocene complexes, understand the interaction of metal with cyclopentadiene by molecular orbital theory, analyze the synthesis of Metallocenes by different methods and study different type of structures of different Metallocenes. Now, let us introduce to you the topic of Metallocenes. The Metallocene term is related to bis cyclopentadiene metal complexes or sandwich complexes, but wide usage is now accepted to include cyclopentadienyl complexes, that is half sandwich complexes as shown in the figure, and multi-cyclopentadienyl complexes or multi-decker sandwich complexes, as well as complexes with additional substitution at the metal center. The metallo prefix can't be used when one considers the development of complexes involving non-metallic elements such as boron, silicon or arsenic. In fact, Metallocene-like complexes are now known for many elements in the periodic table. Here in this figure you can see the Metallocene structure. Now let us study in detail about the cyclopentadiene ligand. The cyclopentadienyl moiety acts as an important spectator ligand and possesses ubiquitous inorganometallic chemistry. It remains inert to most nucleophiles and electrophiles and solely engages in stabilizing organometallic complexes. The cyclopentadienyl ligands are used in the formation of wide array of organometallic compounds. These compounds exhibit different formulations that begin with the so-called piano stool or the CPMLN, where M is the metal center, Cp is the cyclopentadienyl ligand, N is equal to 2, 3 or 4, N is the number of ligands or L. And most commonly observed Metallocene Cp2M type, and the other is bent Metallocene Cp2MXN, where N is equal to 1, 2 or 3 again. In the piano stool type compounds having the structure CPMLN as described to you just earlier, the cyclopentadienyl ligand is regarded as the seat of the piano stool, while the remaining L ligands are referred to as the legs of the piano stool. As you might have seen, the piano stool on which the piano player plays the piano. Though the cyclopentadienyl ligand often binds to metal in N5 or the eta 5 or the pentahepto fashion, for example as in ferrocene, the other form of binding to metal at lower hapticities like that of the eta 3 trihapto binding, for example as in eta 5 Cp or that is the cyclopentadienyl or eta 3 Cp, tungsten CO whole twice, and that of eta 1 that is monohapto binding as in the case of eta 5 Cp that is eta 5 cyclopentadienyl or eta 1 Cp iron CO whole twice complex, are also seen on certain rare occasions. The binding modes of the cyclopentadienyl ligand in metal complexes can be ascertained to a certain degree by proton NMR in the diamagnetic metal complexes in which the cyclopentadienyl protons appear as a singlet between 5.5 to 3.5 ppm, while the beta and gamma hydrogens come between 7 to 5 ppm range. Let us now talk about the interaction of cyclopentadiene with metal. We can understand the interaction of the cyclopentadiene and metal through molecular orbital diagram. The frontier molecular orbital of the cyclopentadienyl ligand contains 5 orbital, that is Psi1 to Psi5, residing in 3 energy levels. The lowest energy orbital Psi1 does not contain any node and is represented by an A1 state followed by a doubly degenerate E1 states that comprise of psi2 and psi3 orbitals, which precede another doubly degenerate E2 states consisting of psi4 and psi5 orbitals. Now you can see here in this figure clearly we have shown you the molecular orbital diagrams of the cyclopentadienyl ligand, and you can see the various psi1 to psi5 orbitals. The above frontier molecular orbital diagram becomes more captivating on moving over to the metallocenes that contain two such cyclopentadienyl ligands, especially in the Cp2m system. For example, as we discussed or mentioned earlier for ferrocene. Each of these above 5 molecular orbital of the two cyclopentadienyl ligands combines to give 10 ligand molecular orbitals in 3 energy levels. Generic Metallocene Cp2m type complexes are formed for many from across the first row transition metal series along scandium to zinc. The number of unpaired electrons thus correlates with the number of unpaired electrons present in the valence orbital of the metal. The manganocene exists in two distinct forms, one in a high spin form with 5 unpaired electrons as in Cp2Mn, that is manganese with 2 cyclopentadienyl ligands, and the other in a low spin form with 1 unpaired electron as in Cp*2Mn, owing to the higher ligand field strength of the Cp* ligand. Another example is cobaltocene, represented by Cp2CO, which has 19 valence electrons and thus gets easily oxidized to the diamagnetic 18 valence electron species Cp2CO monopositive. Now I would like to talk about bent metallocenes. Bent metallocenes are represented by the formula Cp2mxn type complexes formed of group 4 and other heavier elements of groups 5 to 7. In these complexes, the frontier doubly degenerate E2g orbitals of the Cp2m fragment interacts with the filled lone pair orbitals of the ligand. Now here we have shown you the bent metallocene structures and their molecular orbital diagrams also in this figure. Now having talked about the structure of metallocenes and given you the introduction of the same, let us now foray into the discussion of synthetic procedures of metallocenes. The metathesis reaction is widely used in the synthesis of metallocenes. The alkali metal cyclopentadienides, magnesium dicyclopentadienides and thallium cyclopentadienides are important synthetic sources of Cp- ligands. This and other generally applicable methods as well as specific reactions used for particular complexes are classified in the coming discussion with key examples, and synthetic procedures will also be discussed for particular complexes. Now here you can see these are the various reactions using cyclopentadienes. According to the first equation here you can see the cyclopentadiene carries a relatively acidic proton and reacts smoothly with a number of the more reactive main group elements such as sodium and magnesium, and certain metallocenes can be prepared by co-condensation of the cyclopentadiene with the element. Having a look at equation 2, that has been extrapolated to other Cp- derivatives and applies to other organometallic reagents such as dimethyl magnesium and the methyl derivative of aluminium, that is hexamethyl aluminium. The metallocene compound of sodium or potassium metal can be obtained from the reaction of the element hydride with cyclopentadiene. If you look at equation 3, or the reaction of the element imide with the cyclopentadiene in liquid ammonia, equation 4 describes a similar imide displacement reaction which is used for the chalcocene or barocene derivatives. Second method of synthesis is the salt metathesis reaction. Now here we have given you certain equations and we shall discuss these. Salt metathesis reaction is mostly generally applied procedure for the preparation of metallocenes involving the elements of group 2, 13, 14 and 15, and in an appropriate stoichiometric combination of an element halide or polyhalide with an alkali metal cyclopentadienide salt, usually lithium or sodium, or a magnesium dicyclopentadienide salt. Complexes of aluminium and gallium involving the element in less familiar low oxidation states are obtained from metastable halides, which is AlCl, that is the aluminium chloride, monochloride, and the gallium monochloride, which are formed in situ. The third method is the disproportionation, comproportionation and decomposition reaction. Now the equations are clearly shown here. This method is useful for the synthesis of Metallocenes and its methylated derivatives by thermal decomposition of CpMgBr, that is a cyclopentadiene magnesium bromide. The comproportionation reaction used to obtain substituted derivatives of half sandwich complexes for magnesium, germanium and tin. Reductive elimination of cyclopentadiene ligands from Cp3 indium complex and of phenyl groups from Cp2 lead diphenyl complex is also thermally induced. The fourth method of synthesis is halide ion abstraction. The equations are shown to you here. The procedure used for the formation of half sandwich complexes in which N is equal to 1 of boron, germanium and tin, and the sandwich complexes in which N is equal to 2 of arsenic, antimony and bismuth. The next method describes the substitution onto the Cp ligand frame. As you can see, the equations are shown to you here. Thallium and tin metallocenes have a relatively high stability, which allows for modification of the cyclopentadiene ligand with the retention of the complex. The procedure useful for the preparation of a particularly extensive series of stanocenes, including Cp- ligands bearing silyl, stenyl, phosphine or phosphinium moieties, and is responsible for the formation of novel Cp tricyanovinyl thallium complex. Another method is the reduction method. The equations are clearly shown to you here, students. Reductive dehalogenation can be used for silicon, germanium and tin in Cp*2ex2 form complexes and for aluminium in the Cp*AlCl2 whole twice and for Cp thrice indium complexes, and also for the Cp whole twice lead diphenyl complexes, which can be thermally promoted. The next method involves the addition of cyclopentadiene anions, and the reaction is shown to you here. Anionic multi-cyclopentadienyl complexes can be achieved by the addition of cyclopentadienide anions onto lithium, sodium, cesium, thallium and tin. This is achieved by reaction of the neutral metallocene with sources of nucleophilic cyclopentadienide in salts with complex cations such as tetraphenylphosphonium and tris-dimethylaminosulfonium. Now, after having discussed the synthetic schemes for the synthesis of metallocenes, now I will discuss the structural type of metallocene complexes. The structure of main group metallocene chemistry are varied with the position of the element with respect to the cyclopentadienyl ligand and the number of such Cp ligands associated with the element center and their relative orientation. The involvement of auxiliary ligands, that is other than the Cp derivatives, with the element and the association of the complexes into dimers, oligomers or polymers. The general cyclic fluxionality of the Cp ligand implies that all 5 of the carbon atoms in the Cp' frame are involved in the Cp' element pi interaction and systems exhibiting low hapticity. The non-equivalent element carbon distances obtained from the X-ray crystallographic data often illustrate a closer interaction to some framework carbon atoms than the others. This can be defined by the similarity or difference between the Cp' centroid E distance and the Cp' plane E distance. Now here we have shown you in this figure the Cp' centroid to E distance and the Cp' plane to E distance in the complex. Now we shall discuss about the sandwich complexes. As shown by the term, sandwich compounds represent the prototypical metallocenes and they involve two Cp' ligands, one on either side of the element. There are many complexes and examples of sandwich complexes with the two ligands planes parallel as shown in the figure. Usually staggered D5D and eclipsed D5H conformations are preferred. Also examples of sandwich complexes with the two ligand planes non-parallel or often referred to as the bent sandwich structure complexes are also seen in this figure. Most sandwich complexes involve an equivalent interaction with the Cp' ligand, that is lithium Cp5Bz, that is a benzyl, is a rare example of the asymmetric coordination of two Cp ligands with the lithium as the central metal atom. Next is the half sandwich complexes. Many elements are available for complexes by using single pi coordinated Cp ligand as shown in the figure, in which Y is related to the non-bonding electron pair, a covalent bond, substituent R, or a dative covalent bond as in the auxiliary ligand. The formation of molecular half sandwich complexes of the element depend on the valence and the size of the element. The most widespread series of complexes are known for lithium of the form Cp3T lithium.THF, that is tetrahydrofuran, and beryllium Cp beryllium chloride complex, and the cationic systems are accessible for boron, for example the Cp star boron bromide, and along with aluminum bromide, that is with the 4 bromide atoms. As shown to you here, various half sandwich complexes are drawn in this figure. Now we shall discuss the structural aspects of pi cyclopentadienyl molecular complexes. Association of element centers by pi bound mu Cp' ligands is a general feature of polymeric structures. It also shows that the neutral Metallocenes bound together by an additional cyclopentadiene anion in a molecular anionic system. As shown to you in the figure, the general formula is E2Cp3 is observed as a non-parallel multi-decker sandwich for cesium and thallium and plumbocene sandwich units, represented by Cp2 lead. They are associated in the unusual anions of Cp5Pb2 and Cp9Pb4 type structures. Each lead center accommodates 3 cyclopentadienyl ligands as in the tris cyclopentadienyl anions, which are known for both tin and lead in the salts such as magnesium tetrahydrofuran whole 6 and the Cp3E whole twice. Next is the structural aspect of mu pi cyclopentadienyl super sandwich polymers. The polymeric arrays for alkali metals cyclopentadiene by half sandwich formulation involving the alternating element and the mu pi Cp ligands. The planes of the Cp' ligands may be parallel or almost parallel, referred to as super sandwich, as in the case of lithium Cp, or the sodium Cp or non-parallel as for potassium Cp complexes. The branched polymeric structure observed in the solid state for the sandwich metallocene, such as the Cp2 lead, reveals a tri-coordinate environment for each lead center composed of 2 mu pi cyclopentadiene ligands, shown by the dashed lines in the next figure, and 1 terminal cyclopentadiene ligand shown by a full line. As you can see here, it is clearly shown in the figure. Now let us discuss about dimers. The dimeric arrangements are observed in the solid state for Cp5Bz indium and Cp5Bz thallium, one of the 2 crystalline forms. More familiar dimeric structures involving halide bridges with the terminal half sandwich Cp' complexes, as shown in the next figure, where X is the halogen and Y is the halogen or the donor, are adopted by compounds of magnesium, calcium, aluminium and bismuth. Now we shall discuss a little about clusters. the complexes of group 13 elements shown by the structural formula of CPE, which are monomeric in the gas phase and take on highly symmetric cluster arrangements in the solid state. A tetrahedral structure is observed for Cp star aluminium, while Cp star gallium and Cp star indium adopt octahedral hexameric structures. A hexameric cluster structure was observed also for the Cp whole twice thallium compound or the complex, but involves only a mu pi Cp interactions between element centers as shown clearly to you in the figure. Now students, we have discussed many aspects of metallocenes in this particular module. I shall now like to summarize this module for you. In this module, we have taught you that an extensive series of main group metallocene complexes have now been identified and comprehensively examined. Most elements of group 1, 2, 13, 14 and 15 engage in the cyclopentadiene dash or Cp dash ligands in a pi interaction. A wide structural diversity observed in metallocenes by a relatively weaker Cp-E bond. Flexible Cp-E interaction and the ability of Cp- to behave as a leaving group, allowing for an extensive substitution chemistry. Further diversification involving isolobal analogues of Cp- has already begun and represents the future of main group metallocene chemistry. So, I hope you understand and you appreciate the structural aspects and the chemistry of metallocenes in a big way starting from now in a chemistry world.